Hello, my name is Edward, and today I will be doing question 19 from the sprint round of contest 12301. Question 19 reads, if the sum of the positive factors of n, which is the product of a and b, is given by the formula 1/2 times the quantity 2a minus 1 times the quantity 3b minus 1 for some positive integers a and b, compute the 10th smallest possible value of n. And our answer choices are 27, 16, 18, 12, and all of the other numbers that we can think of. So in another way of trying to describe this problem, we want to find a pair of factors of n, which we'll call a and b, that will satisfy this formula. So instead of saying this formula over and over, let's just call this formula S. So S is by definition the sum of the positive factors of n. Another big hint of this problem is that we only need to test the numbers up to 27. If there's only 9 values that work under 27, then we know that the answer has to be something bigger than 27. So it has to be other. But testing 27 values is going to take a long time, especially when we don't know which pair of factors for each number will work. So let's try and find a more general way of approaching this problem. Let's take a smaller set of these numbers and see which ones work. So one set that we could take would be the primes. If n is a prime, then we know that the factors have to be 1 and n in some order. The sum of the factors of n would therefore be n plus 1, since there's only 2 factors. In the case where a equals n and b equals 1, the formula for s gives us 2n minus 1. If we set this equal to n plus 1, we simply get n equals 2. So n equals 2 will work. On the other hand, if we let a equal 1 and b equal n, then we get the formula is 3n minus 1 all over 2, which gives us the solution n equals 3. And we know if n is a prime and it's not equal to 2 and it's not equal to 3, then it will not work. So we can mark all of these numbers in red. Next, we'll test the powers of 2. If n is a power of 2, then the sum of the factors, which are 1, 2, 4, dot, 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 n over 2, n, the sum is simply 2n minus 1 by the formula for the sum of a finite geometric series. S is an integer, so that means that either 2a minus 1 or 3b minus 1 is divisible by 2, since our formula has to give us an integer. But 2a minus 1 is always odd, so it's never divisible by 2. So 2 must divide 3b minus 1. So 3b minus 1 is even, which makes 3b odd. But 3b is the product of 2 integers, so b itself also has to be odd. Then we have that b must be 1 in this case if n is a power of 2, since 1 is the only odd factor of a power of 2. And this makes n itself equal to a. Using our formula, we get s is equal to 2n minus 1, which is the exact same expression as we got manually computing the sum of the factors. So this means that if n is a power of 2, it will always work. It will always be a valid value of n. So we can mark 1, 4, 8, and 16 all down in green. Next, let's test if n is 2 times a prime. So we can write n equals 2p for a prime p. Then the sum of the factors is 1 plus 2 plus p plus 2p, which is equal to 3 plus 3p. If b is odd, which we know b is odd actually, so b, we can have that as equal to 1, which makes a equal to 2p. Then our formula gives us s is equal to 4p minus 1. Setting this equal to 3 plus 3p, we get that p is 4. But this is not a prime, so there is no solution. Recall that we previously defined p to be a prime. Otherwise, b is equal to p, which is odd since 2 is not odd. Then a is 2. So by the formula, we get s is equal to 3 times the quantity 3p minus 1 all over 2. And setting this equal to 3 plus 3p, we get p is 3, or n is 6. So if n is 2 times a prime, the prime must be 3. And the number itself must be 6. So we can mark 6 as valid, and 10, 14, 22, and 26 is invalid. Next, let's test 4 times a prime. So we have n is equal to 4p. So the sum is 7 plus 7p. b is still odd, so b is either equal to 1 or p. in each case, a is equal to 4p or 4. In each case, we get that p is equal to 8, which is not a prime, so there's no solution, or p is equal to 3, which forces n equal to 12. This means that if n is 4 times a prime that is not 3, then it is not a valid solution for n. So we can mark 12 down as valid and 20 as invalid. From here, we found 8 numbers that are possible values of n, so we can test the next few values to see which 2 will work, since we simply want the 10th smallest possible value. We can see that n equals 9 works when a is 1 and b is 9, n equals 15 has no solutions, and n equals 18 has a equals 2 and b equals 9 is a valid solution. So therefore, n equals 18 is our 10th smallest possible value of n, and that is our final answer. But let's backtrack a bit. Let's see if we can come up with another, more general solution for valid values of n. Let's say n is a power of 2 times a prime. So we can write n is equal to 2 to the k times p for a prime p. Then s is 1 plus 2 plus 4 plus dot 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 plus 2 to the k plus p plus 2p plus 4p plus dot 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 plus 2 to the k times p. And notice that we can factor a p plus 1 out of this expression. And the other factor would be 1 plus 2 plus 4 plus dot 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 plus 2 to the k, which from our case where n is a power of 2, this is simply equal to 2 times 2 to the k minus 1. That is a finite geometric series. We still only have 2 cases where b is equal to 1 or b is equal to p, but in fact we can notice that if we let a equals 2 to the k, which is a valid factor of n, then we have that 2a minus 1 is simply 2 times 2 to the k minus 1, which is the second factor of our expression. So this leaves b is equal to p, since n is the product of a and b, which yields a or b plus 1 or p plus 1 is equal to 3p minus 1 all over 2. And this is solved by p equals 3. So this means that if n is 3 times a power of 2, then n will be a valid solution. But this leads us to ask, will 2 times any power of 3 work? Since we can take a equal 2 and b equal to that power of 3, we can see that 6 works, so maybe we can reverse the pair. And in fact, the answer is yes. 18 is a valid solution from our testing before. In fact, any n whose prime factorization is just 2's and 3's will work, because we can write n equal 2 to the m times 3 to the n, then the sum s is simply 2 times 2 to the n minus 1 times the quantity 3 times 3 to the n minus 1 all over 2. Notice that the over 2 part comes from the finite geometric series formula. This leads to a equal 2 to the m and b equal 3 to the n. But this does not show that these are the only numbers that work, since we still have to test those that are not simply the product between a power of 2 and a power of 3. We still have to test 15, 21, and 25 if we want to find, say, the 20th smallest possible value of n. And this is simply because a and b can be any pair of factors. So there could be a random value of n that works by chance. This concludes question 19 from the sprint round of Contest 12301. Thank you guys for watching, and we'll see you in the next one. Goodbye.